I'll give you a warning sometime around 12 o'clock or so, just to let you know, like, probably
Okay.
time to stop for questions.
I'll probably be done before then, actually. I think I don't know. We'll see how it goes.
Okay, I mean, like, take as long as you want, take as short as you want. I know in previous years some people have just, asked questions, had people ask questions, but
Yeah, I don't think it should. This talk should probably last more than 45 minutes.
no, that's about a good amount of time. Whenever you're ready, just let me know. Okay. Hello? Oh, there we go. For our next talk, we'll have Professor Cohen speaking. He grew up in London, and he ended up going to school there in the Slade School of Fine Arts. In 1968, Professor Cohen ended up going over to Stanford as a visiting a visiting professor, and he ended up never going back. In the early 70s, he started working on a project called Aaron, which is basically an artificial intelligence thing that colors things depending on different inputs. So today he'll be talking about that and where exactly Aaron's gone in the last 20 years. All right, without further ado, here he is.
Thank you. I always figured that I could have been a millionaire by the time I was 30 if I'd been interested in money. Of course, life was a lot slower 30 years ago, 50 years ago. But the last speaker has put something in perspective that has sort of bothered me for quite a long time. A long time ago when I was a visiting scholar at the AI lab at Stanford. I was already on the faculty at UC San Diego at that point. But I remarked one day to a colleague there that I was a bit stuck on my work and didn't quite know how to proceed. And he said, well, you declare what you've done to be a success and you move on to something else. Well, it's a sort of advice you give to somebody whose company doesn't quite make it, I guess. I was shocked until I realized that he was actually offering a project-oriented view, not entirely unreasonable in an educational institution whose goal is to turn out well-trained individuals with PhDs in a reasonable time. After all, the last thing you want in that individual is an open-ended project. But I wasn't there to get a PhD, and I wasn't there to start a company, and my project was open-ended by definition. Now, as you well know, computing has turned out to be the great enabling technology of the age, pulling in many people from many fields who have no central concern with computing itself at all. That certainly wasn't the case 30 years ago, when computing was in its infancy, and I must have been seen as something of an oddity by the regulars at the AI lab, one of the very small number of people who saw computing as a way of advancing their own field, which in my own case was, as you heard, art making. Now progress in the arts isn't measured in terms of successfully completed projects. You don't finish one and then look for something else to do. My intuition had told me that being at the AI lab at Stanford would enable my own forward movement as an artist. But actually, if you have some idea what computing was like 30 years ago, you'll recognize that it was at best a long shot. Even so, there was never any question of declaring my program to be a success or a failure and moving on to something else. Win or lose, I was doing what I was doing, and I was committed to going on doing it. So what was I doing? I was trying to write a program that could function as an artist. not as an artist's tool, a kind of, what should I say, proto-Photoshop that I could use to make art. After 20 years as a professional artist, I already knew how to make art. But as an autonomous entity capable of generating original artworks, as autonomously at least as I could figure out how to make it. And I've been trying ever since. If I can figure out how to take the lights down a bit, you might. Can you see the screen okay? You won't see the colour much, I don't think. Do you know how to reduce the light, the house lights? Technology will get you every time. Anyway, that's fine. Thank you so much. Autonomy isn't an absolute, of course, but given that Aaron, that's the name of the program I started while I was at Stanford, given that Aaron makes most of its images at night while I'm asleep, the program is obviously more autonomous now than it was then. Its autonomy doesn't extend to exercising judgment about what it's doing, however, and exercising judgment the next morning, deciding which of the 100 or so images should I print and which should I discard, was by no means easy, remains by no means easy. I'll ask you to take my word for it that they're all good enough to print. But the one thing you can easily see for yourself is that Aaron is now a quite accomplished colorist. And in fact, it's a much stronger and a much more inventive colorist than I ever was myself. Color. Now, that is surely the least like area of expertise for a computer program, especially one without a visual system. There's nothing more fundamentally visual than color for the human animal, in the precise sense that colour is not a property of the real world, it's a property of the perceptual system that interprets the various wavelengths and amplitudes of the light from the real world. Animals that don't have the right kind of retina don't see colour, and a program without any kind of retina doesn't see anything. Curiously enough, our own relationship to colour is quite problematic. We can certainly see it and respond to it, but we're almost incapable of imagining it. You might suppose that's because we're mostly not experts. But no, even expert colorists can't imagine complex colour system relationships. The artist no artist has ever proceeded by constructing an internal representation, an imagined version of a complex colour scheme, and then telling someone else how to evaluate it. Not until now, that is. And as you will see, what Aaron has been given is not at all what one might suppose an imagined scheme to be. The human artist can't really know how an individual colour choice will affect the scheme as a whole until he sees it in context on the canvas. And consequently, he proceeds stepwise, typically, correcting as he goes. He's entirely dependent on visual feedback, and visual feedback is absolutely central to what he does. Aaron has no visual system. No visual system, no feedback. No feedback, no basis for continuous correction. I got a handle on the problem of colour about 20 years ago, after several years of frustrating lack of insight, when it became clear to me finally that if Aaron didn't have the hardware upon which my own expertise rested, then the standard expert system approach of emulating my own knowledge, my own expertise, was a non-starter. I needed to build a system based on the resources Aaron did have, which included, if I could devise a way of representing individual colours, an entirely unhuman ability to build and maintain an internal model of arbitrarily complex color schema. But how to generate those colors? I needed to devise a set of rules, flexible enough and robust enough to apply across the full range of unpredictable compositions that Aaron was capable of generating. That rule-based coloring system served Aaron very well for the next 20 years, but that isn't what I want to talk about. In any case, it's been adequately described in several papers which are available on the web. Enough here to say that in those 20 years, it grew to be a very long and extremely detailed production system, so long and detailed finally that introducing new rules or making changes in the existing rules without breaking something somewhere was becoming more and more difficult. And a few months ago, I replaced the entire system with a quite remarkably simple algorithm that not only performed at least as well as its predecessor, but opened up a much wider range of coloring strategies that had been possible before. It's that algorithmic system I want to talk about. It really is simple. It could have been written in a couple of hours by any novice programmer if he had known what to write. But its structure and its development are so deeply embedded in the technology of color itself that if I'm going to explain how and why it works as well as it does, I'm going to have to start with a little background. So here's a brief review then of what we know about color and about the various ways it can be represented and specified. To begin with, as I said, color doesn't exist in the physical world. What exists in the physical world is light, which varies across the visual field in its wavelength and its amplitude. Color is what we see, the sensations generated by the retina in response to the varying wavelengths, in response to the varying wavelength and amplitude of the light. It follows then that it requires only three variables, the hue, the brightness and the saturation, to fully describe any color sample. And all of them can be represented on the graph I'm showing you here. The hue is where the peak of the sample falls on the visible spectrum. The saturation is the bandwidth of the peak. We call it saturation, brilliant. There are a dozen different theories and they all use different terms. But in any case, it's really a measure of how much of the available energy falls within how narrow a band on the spectrum. And brightness, where the sample would fall on a scale from black to white, how it would be recorded on black and white film, roughly speaking, is simply the total energy of the sample. And it's represented here by the area under the graph. For those of you who indulge occasionally in old black and white movies, or who still use black and white film in your prehistoric cameras, it should be clear that the brightness component provides most of the information we need about the world. And from the perceptual standpoint, it remains far more important than either hue or saturation, even when we're responding to the colors we see. In fact, it would seem that whatever practical purposes were served by color vision in earlier times, it serves a predominantly aesthetic function to modern humans. And for the artist wishing to capitalize on that function, hue, brightness, and saturation are necessarily the terms in which we want to build color relationships. But we can't manipulate these terms directly, and what we can manipulate depends upon the medium. The painter has a wide range of differently colored substances, physical materials, to be squeezed out of tubes and mixed together. The computer artist uses viewing devices of one sort, CRT, LCD, plasma panel, whatever, that generate the color of the individual pixels from the relative settings of the three so-called primaries, red, green, and blue. So you might say that the primary materials for the painter are the variously coloured pigments in the tubes of paint, while the primary materials for the computer artist are red, green and blue. Could the painter manage if he had only red, green and blue paint? Certainly not. The three suffice for the display because mixing them on the display is, as we say, additive. As more of each primary is activated, it adds to the total energy of the result. You get the brightest colour, yellow, by mixing red and green. Mixing paint, on the other hand, is subtractive. Physical materials act as filters, and adding another filter reduces the total energy of the mixture. So mixing red and green paint produces, well, actually it's still sort of in the yellow part of the spectrum, the yellow-orange part of the spectrum, but it's in fact so degraded that we're going to call it something else. Now, when I started to write the colouring rules for Aaron, I accepted that my primary materials were determined by the output device, the screen. So the output side of each rule would have to be an RGB, red, green, blue, specification that satisfied the desired relationship of the three primary characteristics of the colour, the hue, the brightness and the saturation, within the colour scheme as a whole. As you may imagine, finding two RGB mixtures that satisfied the desired relationship of all those three characteristics was non-trivial, indeed sometimes not even possible, and it took years for me to acquire the level of expertise in manipulating this RGB system that I'd had in manipulating paint. In any electronic display system, everything comes down to red, green and blue. But as a way of specifying what is to be displayed, fortunately, RGB isn't the only game in town. My work on the new system began, in fact, with the intention of stepping back from the direct specification of the three RGB primaries and adopting a mode more in line with the more general way of describing and manipulating colour, that is, by its hue, saturation and brightness. Fortunately, the Lisp system which I use also has what's called an HLS mode, which allows colour to be specified in terms of its hue, lightness and saturation. And it was only when I started, that sounded exactly like what I needed, and it almost was. It was only when I started to rewrite Aaron's colouring rules to provide HLS output that I realized that the lightness component in HLS wasn't, in fact, quite the same as my notion of brightness. Here's a physical model that would explain, that makes clear what HLS actually means and why lightness and brightness aren't quite the same thing. As you see, you can think of HLS as a system in which a filter of some hue sits between a light source and the viewer. Lightness is a measure of the energy of the light source, and saturation you might think of as the thickness of the number of sheets in the filter. In my hue, brightness, saturation model, brightness represents the level of light energy which arrives at the viewer's retina, what the viewer actually sees after it has passed through the filter. In the HLS model, lightness is the available energy of the light source itself before its brightness is reduced by a filter. Well, no big deal. The difference wasn't critical. After all, the behavior of light doesn't change because one adopts a new way of describing it, but it was obvious that lightness and saturation were both involved in determining brightness, and consequently that they couldn't be considered separately. What was much less obvious was how the resultant perceived colour would be affected by different combined values of lightness and saturation. It took me a while to develop a good intuitive grasp of how that would work, and I couldn't rewrite Aaron's rules without having that grasp. As as things turned out, though, I didn't, in fact, rewrite the entire rule base. Because long before I'd finished the job, I started to suspect that there may be a quite different way of going about things. I was motivated in part by a growing discomfort about what I was beginning to see as a hard limit on Aaron's autonomous expertise, the fact that whatever expert knowledge it had only implicitly, available to it only through the rules I wrote. I thought it should have that knowledge available in explicit form, and consequently I saw one of the first tasks in building a new system to provide some of that knowledge. Let me explain that. If you look closely at any of Aaron's images, this is a detail, for example, you'll find that every single patch of colour has in fact three components. There's a main colour, and then there are two variants of that colour which are used for the edges of the form, offset from it to some specifiable degree in any or all of the three primary characteristics. Rather than specifying the actual colours to be used, as I'd done with the RGB-based system, I thought it should be possible to say something like, under such and such circumstances, shift the hue barely perceptibly for part of the edge. And of course it is possible, provided that the program knows what barely perceptibly means. Well, what does it mean? Assuming that the spectrum is approximated by 360 colours, each of which is mixed from only two of the three primaries, let's define the minimal perceptual shift for any colour to be the number of steps you need to take on one side or the other before you begin to notice a difference. And that turns out to be anything but constant as you move along the spectrum. You may not be able to distinguish between colours 2 or 3 steps apart in some places, where in other places the difference between two adjacent colours sticks out like a sore thumb. As you may imagine, assembling this minimal perceptual shift data, that's where this slide comes from, was really no fun at all. 360 different colours, and we're only talking there about the spectral colours, the 360 spectral colours, and not at all about mixtures of all three. It was a critical issue in the design of the first algorithm, the first algorithmic version of the program, which is as I announced it to be in the abstract for this talk. But you know, one tends to write abstracts before one has written talks, and in this case even before I'd done the work, or much of the work. And if I'd written the abstract more recently, I probably wouldn't have mentioned it at all, because I'm up to version 3 now, and it doesn't really figure as much of an issue any longer. The change from the center of a colored patch to its edge is now controlled throughout the entire process by a single contrast variable, and that seems to work just fine. What has emerged as the central driving force behind the first version, though I could hardly have expressed it at the time, was the dawning suspicion that one could only go so far in developing a colour scheme by picking individual colours, because a colour scheme is characterised by the relationships between the colours, and that one would need to focus directly upon the nature of the relationships rather than on the individual colours themselves. So in designing the first version of the new system, then, I provided only for the relationships of colours in terms of their hue, lightness and saturation, bypassing entirely the kind of specification for individual colours that had characterised the earlier system. Hues were determined by subject matter. I should explain that Aaron's recent work tends to teeter on an edge between figuration and abstraction, but all of it is in fact based upon plant growth. It didn't much matter what hue the program chose for what it would regard as leaves or flowers, but the distance between the hues for different elements, flowers, tendrils, branches, and so on, did matter. And to fix those distances for Aaron's entire output, I settled on an additive series shifted to some random starting point in the 0 to 360 of the colours available. The hues available. Every image would then have the same spacing, but no two of them would have the same colour. For the lightnesses and saturations to be associated with each of these hues, the program simply generated two lists of random values. These were then the only values that could be used for the entire image. And as each plant element came up for colouring, its hue would be predetermined according to subject matter, and its lightness and saturation would be drawn randomly from their respective lists of values. If there are 7 object-related hues allocated to an image then, and 7 values in each of the 2 lists, each hue can appear in any one of 49 variants, and the colour scheme as a whole could involve almost 350 distinct colours. So, although all the leaves of a tree would have the same hue, no two of them were very likely to have the same colour, just as no 2 leaves on a real tree under real lighting conditions would appear to be exactly the same colour. It could hardly be simpler. It's so simple it would be laughable, but for the fact that these half-dozen lines of code worked at least as well as a heavyweight expert system that had been refined continuously for more than a decade. Evidently, limiting the lightness and saturation to a small set of fixed values provides coherence to the colour scheme as a whole, though the basis for that coherence is anything but evident to the viewer. What do I mean when I say that it worked at least as well as its predecessor? It may not be entirely obvious to people in the engineering disciplines, but in the art-making game, we don't think about finding the best solution to a problem. We think about generating the widest possible range of excellent solutions. One limitation of that range for me under the old system of handmade RGB rules was that it almost never produced greys. Strange. But to generate greys in the RGB system, you need close to equal amounts of red, green and blue, and I always found that difficult to do while satisfying all the other requirements. Now, if you look at my HLS model, you'll realize that 0 saturation means literally that there is no hue, no filter, no color. And you have a neutral grey controlled entirely by the lightness. With the new algorithm then, the inclusion of variously neutral greys in a color scheme simply depended on what numbers were in the saturation list and which ones were selected for individual colors. And it quickly became apparent that from the same set of numbers, the algorithm could generate a much wider range of color schemes than its predecessor could. Not only schema with both very pure and very grey colours, but also some strange, almost monochromatic compositions, quite unlike anything Aaron had ever generated. Well, so far so good. A much extended range, generated simply by the numbers in a couple of randomly put together lists. But just where on that range a particular image would fall was random, just as the numbers were. I thought the program should have some degree of control in the matter, that it should be able to choose where on the range it wanted to operate. By this time I had a more developed sense of how the various settings for lightness and saturation determine the kind of color they'll generate. At one end, with both lightness and saturation close to their maximum values, we get relatively pure colors. At the other end, when both of them have very low values, it means there's very little light and very little hue, so we have essentially dark greys. And in between, we can vary the brightness of the greys by varying lightness while keeping the saturation constant, or we can vary the greyness by leaving the lightness alone and varying the saturation. And in the middle we have both lightness and saturation somewhere in the middle of their range of values, and we get a palette of muted colours, not too saturated, not too light, and not too dark. So while picking random values for lightness and saturation generates a lot of different colouring possibilities, evidently controlling that range means controlling the ratios of those values. So let's suppose now that instead of simply using pre-selected random numbers for lightness and saturation, we distinguish between 3 ranges of values for each of them. The high value set may contain random numbers, as you see here, say between 0.8 and 1, the middle range between 0.4 and, as you see. Then we have 9 different ways of pairing the ranges, 9 combinations of lightness and saturation ranges, each of which will give rise to a different kind of colour scheme. Now, we're unlikely to use all 9 of these combinations in a single image. That would be tantamount to just doing everything randomly. And what we certainly don't want is a composition controlled by just one of them. Why? Because an image composed of exclusively spectral colours is apt to look crude rather than vivid, just as an exclusively light colour scheme will look weak rather than subtle. The vividness of a colour is most effective in the presence of more muted colours, just as light colours need some dark colours around to focus attention on how light they are. So we probably want 2 or 3 of these range pairs, but we need to control how much each of them gets used within a single image. And if we want to get the widest gamut of outcomes from any particular If we want to get the widest gamut of outcomes from any particular set of combinations, we don't want the mode of control to be too deterministic. We don't want it, for example, to apply a low-low combination every 4th time with a high-high combination all the rest of the times. Rather, we want to specify only the average frequencies with which each gets chosen, leaving it to chance to determine which will actually be used for any particular composition. Actually, that has long been Aaron's way of making choices, calling a preference function that looks rather like this, that guarantees only a statistical likelihood that, in this case, A will be returned 60% of the time. That is, if a number between 0 and 100 is less than 60, and so on and so forth. The new version, using essentially the same strategy to select values from predetermined range combinations, looks rather like this, very much the same. It uses a script, where the first character of each range symbol indicates the lightness range and the second character indicates the saturation range. So if the HL range is selected, for example, the lightness will be randomly selected from its high range and the saturation from its low range. That brings us on then to the second version of the algorithm. Once again, it has 2 phases, a preamble in which the various controls are set up, and a development in which these controls are applied element by element until the image is complete. As before, the first step in the preamble deals with the spacing of hues. A sequence of numbers is randomly located somewhere on the 360-point circle. And as before, the resultant hues are assigned to the different elements, leaves, tendrils, and so on, of the composition. 3 ranges of randomly selected values are then assigned to lightness and saturation, 1 each for the high, medium, and low values. As with the first version, these then constitute the only values permitted for the entire composition, but in this case the selection is further restricted to the specified ranges. The final step in the preamble is to compose a preference script, which will determine subsequently how those ranges get selected. A script that looks like this one specifies that in the subsequent development stage, 4/9 of the time both lightness and saturation can use values from their high ranges. 1/3 of the time lightness should be high and saturation low, and 2/9 of the time lightness should be low and saturation high. Again though, let me stress that 4/9, 1/3 and 2/9 represent preferences, not absolutes. Though given a large number of selections required in a complex image, I assumed that the distribution of ranges would average out quite close to their preferences. Well, in practice, they weren't as close as I thought they would be. But more to the point, the intent of the algorithm wasn't really to control how frequently the various range combinations would be selected, but rather to control the distribution of the different ranges of lightness and saturation within the physical structure of the image, the amount of space, that is, that would accrue to each one. That's quite different, of course. And in making its preference-based selection in that second version of the program, it was quite indifferent as to whether it was about to color a very large leaf or a very thin branch. And that led then to the third and the current version of the program. It still doesn't concern itself with the size of an element when it's selecting a color for it, but now it keeps track of how much space actually gets used by each of the range pairs in the coloring process. 80% of the time it uses regular frequency-based selection for the next area to be covered, but every fifth time it compares the use records of all the active range pairs to the usages called for in the preference script. I don't know whether you can see clearly enough, but the last three columns there represent respectively the numbers called for that they've been converted to reals for each of the ranges. The one from last is the current usage, and the last row represents the discrepancy between the two, which, as you see, remains quite low. And in fact, what happens is that the numbers, the lowest, the range pair that shows up as falling furthest behind its frequency-based selection falls furthest behind its specified frequency is the one that's chosen for the next area to be colored. And as I say, and as you can see from the numbers, the strategy works surprisingly well, with usage remaining remarkably close to the preferences. But more importantly, it means that the kind of color produced is much more predictably linked to the preference script that generated it. Well, a simple change to a simple algorithm for a significant improvement. But of course, you computer science people will already have spotted the fact that what I'm presenting here as a simple change of strategy has actually changed the very nature of the algorithm in a fundamental way. Indeed, I'm not even sure whether the term algorithm properly applies now to programs that are required to sample and evaluate data from an unpredictably developing domain in order to keep them on track. Well, that's pretty much the whole story to date. At least it's the whole story with respect to color. I need hardly add that it's only part of the larger story of how Aaron generates its images. I haven't even mentioned how Aaron generates the forms it uses or how it controls composition. And there are many factors that profoundly affect the way its images are read, even affect how the color is perceived. I mentioned earlier, for example, that our dealings with the visual world rest predominantly upon brightness perception. One corollary of that dominance is that color inevitably slips into a secondary role as soon as the viewer recognizes an image to be representational. In the extreme case offered by portraiture, for example, colour takes on a merely descriptive role used in identifying the sitter. That loss of centrality isn't so big a problem for the current program. After all, it teeters on the edge between representation and abstraction precisely to avoid the problem. Even so, there are distinct differences in reading when the branching structure is very much in evidence compared to those cases where the branches are almost entirely hidden. So similar issues arise with respect to the maximum size the program allows for any single element compared to as compared to when the shapes get bigger, and also by there's the opposite, and also by how much space it decides to allocate to each individual tree in the composition, thus controlling effectively how fully or how sparsely the frame is to be filled. Even the proportions of the framing rectangle plays its part in determining how the viewer identifies what he sees and how he prioritizes his perception of its elements. So in conclusion, here are a few images that were made by the program a few nights ago. It made 129 images in the course of the night, and it was still at it when I interrupted it the next morning. Then it took me almost the same amount of time to examine all the images and discard most of them, and I was quite unable to get the remaining number down below 30, even though I knew that only a few of those 30 would ever get printed. If, as I've said, the goal in the arts is to generate a rich output of excellent work, not to find a single best solution to some problem, then I clearly have no reason for discomfort on that score. From the standpoint of increasing autonomy, on the other hand, there are reasons for some residual discomfort, mostly in the fact that I have to provide Aaron's preference scripts, just as I've provided the crucial limits within which the values for the three ranges for lightness and saturation are randomly set. Clearly, there's a very large number of possible scripts, and I could spend a great deal of time investigating just a few of them. I think it's time I got some help from Aaron. It can generate new scripts easily enough, obviously. In fact, it was generating scripts randomly the night it made these last 5 images. But that won't help much unless I can tell the program how to assess the effect of those scripts upon its own output. Well, I haven't figured that out yet. Just as I haven't yet figured out how Aaron could assess the 100 images it makes in the night and tell me which of them are most worth printing. But I'm working on it. Thank you. You want to put the lights up? That's gone out now.
All right. If anyone wants to ask Professor Cohen questions now, please feel free to do so.
I have a question about when you're generating, you said that the form of a lot of these shapes is based on, and I very much saw that they're based on like plant branching and stuff. How do you represent, I guess, the algorithm that you use to represent this botanical branching? What is that algorithm's basis? What does it draw?
Well, it really rests upon a description of how plants grow, not a description of what they look like.
Okay, so it's like a fractaline, sort of the fractal base?
No, not at all. I'm not smart enough to understand fractals, and I don't like what they look like anyway.
Okay.
No, it's simply, well, let's think about it. A tree starts with a single thing, which will have a length and a breadth, and then it will have some number of branches at the node. The breadth is likely to diminish as it goes up. The length is likely, but not always, to diminish in some cases will get longer and then get shorter again, they won't necessarily be straight, and the further they get from the vertical, the more they'll tend to. So you can describe how the thing actually grows, and construct one from scratch every time. The same is true for the way it generates leaves. A leaf is a central stem with things coming out, and then there are various ways for the edge to form around the thing. So
Controlling.
yeah, that sort of thing. But there isn't a single description of what one looks like anywhere in the program.
Okay.
Hmm?
Is this evaluation of the program, having Aaron evaluate its own work, would that sort of be a feedback loop, like the same as a painter painting a painting?
So
If I knew the answer to that, my boy, I don't know. I don't. The problem is, let's see, what is the root of the problem? Is that when I'm evaluating the thing, I'm evaluating it in terms of what I'm seeing there. The program can't see what it's done anyway. What it has is a list of, a big, fairly complicated data structure that contains data about, for example, the lengths of the different parts. Has quite a lot of detailed information about the distribution of colors. But which of those corresponds closely to the ones that I think are marvelous? They're all good, but it's like a sort of bell curve distribution where, most of them are sort of good ones in the middle, and there are some really odd ones out on the end. It's really the odd ones out on the end that if I have any clue about how to proceed now, it would be to look at a large number and isolate the ones where several key values fall out on the end and see whether they are in fact equated to the ones I find interesting. If so, then I'm onto something, and if not, I have to think of something else.
It occurs to me that if you codified how to evaluate the artwork, you put a lot of art critics out of business.
Sorry?
It occurs to me that if you codified how to evaluate the art, you put a lot of art critics out of business.
Oh, that would be nice. I'd like that.
About your color scheme. From the models that you presented, you have one saturation peak. Do you mix colors in Aaron, or each color selection limited to one saturation?
do you mix colors in Aaron, or is the color selection?
No,
limited
the
to one
coloring is done by
saturation?
the program.
You have one hue. The model you presented had one peak for hue. Do you use more than one, or do you mix colors up, or are they just single peak colors?
Do you use more than one peak for a hue? Like, how in your example you had like that one peak. Are there ever times when you mix colors inside of Aaron, or?
Maybe we're talking at cross purposes. I don't mix colors at all.
Okay.
All of the coloring is done by the program.
Well, that's what I mean. Does Aaron have combination colors, or is it simply one hue?
Oh, okay, got you. No, it always has to assign a saturation and a lightness to any hue. But of course, under some circumstances, it might pick a full value for each of those two, and you'll get a spectral color.
Okay, good. That's what I
Okay, yeah.
Why Fibonacci? When you were doing the hues, I think it was, you picked a random number and you had Fibonacci numbers starting at 13.
He was wondering why when you're picking hues, you had Fibonacci numbers starting at 13.
Oh,
Why you
I was
chose
trying to
that.
figure, I've always had a predilection for the Fibonacci series. But of course, if you start at the beginning, you start with colors immediately adjacent to each other. So I sort of went up the scale a little. Actually, Fibonacci works for any two starting numbers. It always eventually comes to the same proportion.
What response have you gotten from colorists out there when you showed them your Aaron's work? Do they resist it? Do they notice anything wrong? Do they like the
Well, most people in the art world won't believe that it's been done by a program. You know, I always have, when I'm talking sometimes to art audiences, particularly when I'm talking to art audiences, I have to go through it painfully, step by step, to keep insisting, no, I didn't choose the colors. Okay? You know, anybody who's been involved in colorist is going to tell you that this is a world-class colorist. It's not a trivial little program that sometimes works okay. But as I say, I have a lot of difficulty for people who have no background in computing to believe that they don't even know what I mean when I say that the program is doing everything. So it's a bit difficult. But nobody's ever told me, no, I think the color's rotten.
You mentioned that Aaron's work tends to follow a bell curve. Is your goal to make it flat, or?
No, I would just assume that the marvelous stuff I think I'm going to find out there on the end is going to move into the middle, and I'm going to find even more marvelous stuff out there on the end. Let me be honest, I have no idea how to go about doing this. But then I didn't have much idea how to go about it when I started 30 years ago either.
Have you considered ways for extracting characteristics from other images and then using those as a basis for the images that Aaron generates?
No, partly because I'm really not interested, and partly because it's a great deal more difficult than you think it is. Evaluating any visual field, I mean, anybody who's been in vision, computer vision, knows that even trivial problems like can I spot the block in the middle of the floor is a difficult problem. You know, back in a long time ago, people were telling me, well, you know, you should give Aaron a visual system, then it could see. Yeah, come on, I don't have the next 20 years to spend solving vision problems. Looking at another work of art, the ones you like, oh, you know, I think that one's marvelous. What do I think is marvelous about it is no different from the problem of looking at my own, Aaron's, and saying which I think is marvelous. Very difficult problem.
Has the evolution of programming languages over the last 30 years affected how you deal with Aaron?
Yes, in fact, I never talked about that. The breakthrough on color, I mean, I spent a lot of time banging my head against the wall. Didn't know at all how to go about dealing with color. Up till that time, I'd been programming in C. And the change came, the insight as to how to move came when I took the advice of all my friends in the AI world and switched to Lisp. I'm not a salesman, but I heartily commend Lisp to anybody who thinks they're going to do something interesting.
All right. Well, if there are no further questions, let's go ahead and thank our speaker one more time.